So I wanted to walk you guys through the fourth activity. Now, when I say walk through, I'm gonna try to talk. I am going to do the first one sample Z test live, for lack of a better term, and then I'll leave the remaining problems of the activity up to you all to complete. So what I'm going to begin with is something that I always do, and you can see here in the one sample Z test example that I've already done this, but one good thing to do is to always write out the information that the question provides you. So I see that the population mean is 45. The population standard deviation is 12, and alpha is set at 5% or 0.05. The sample mean is 48. Sample size is 250, and it is a two-tailed test. Excuse me. Okay. So we're going to be doing the 4 steps as well as calculating Cohen's d. So I'm going to start with stating the hypothesis. In fact, I'm going to stop sharing so I can just show you my board. It'll be easier to see. So this is what I have so far. I have all the information that was on the question, and now I'm going to start with the stating the hypothesis with the null and alternative. So the null hypothesis always says that these two groups are equal. Now, this question isn't really specific in terms of what populations that we're looking into here, but rather this is kind of meant as a way to get the steps down, make sure we're doing it correctly. So again, we start with the null hypothesis, which is mu equals 45. And the null hypothesis states, since it's a two-tailed test, mu does not equal 45. Now, if we had more specifics on this question, we see that our sample mean is 48. What this mu equals 45, mu does not equal 45, is we are trying to use our sample information, this 48, to generalize to whatever population this 48 belongs to and see if it is equal to the population mean that's been provided. So this mu equals 45 and mu does not equal 45 for the alternative hypothesis is not referencing this mu. It's not referencing the population mean that the question provides, but rather the population of the sample, and which is what we're generalizing for. Okay. So step 2 for hypothesis testing is to state the criteria. So we see that alpha equals 0.05, and we have a two-tailed test. Okay. Now, for one sample Z tests, which we are computing right now, we're finding the critical values. That's part of having the step 2 of setting the criteria. So our critical values, I'm abbreviating it as CV on here for critical values. That's always going to be the same based on those two factors of what is your alpha and what tail test do we have. Oh, there's like a gnat flying on my face, drives me bonkers. Anyway, so I know that for all one sample Z tests, when we have alpha of 5% or 0.05, and we have a two-tailed test, the critical value will always be plus minus 1.96. Okay, so now we get into calculating the test statistic. In this case, the statistic that we are calculating is Z. So we have, first we have to take the standard error, which is population mean divided by the square root of n. And then we plug that into our formula of sample mean minus population mean divided by that standard error. So let me just kind of do that. Okay. So I start with this standard error. So our population mean is 12. So I have 12 divided by the square root of n, which is 250. So usually when I do this, I round to 2 decimal places as I go along. For example, I can't do the square root of 250 in my head. That's just not in my wheelhouse. That's not in my quick to access capabilities as my human beingness. Anyway, so this is, I find the square root of 250 and I get 15.81. Now I'm rounding that to 2 decimal places, that 81, but really it's 15.8113. But I have rounded that to make it a little easier on myself to 15.81. So I've gone from 12 over the square root of 250 to 12 divided by 12.81. All right. 15.81, excuse me. Alrighty, so now let's do that. So 12 divided by 15.81, that gives me 0.75901, blah, blah, blah. So I round that to 2 decimal places to 0.76. So I have 0.759 there, and I round that to 0.76. Keep in mind, if you're using Excel to calculate these things, you're going to have a slightly different answer than me based on how you round it. Again, I'm showing you exactly how I round it. You see that I've rounded it to 0.76. That is not the precise answer, but just for the sake of simplicity, that's how I'm doing it. Okay, so now that I have my standard error of 0.76, now I go back to the Z formula where it is sample mean minus population mean divided by standard error. So again, our sample mean was that 48 minus our population mean of 45 divided by the standard error that we just calculated of 0.76. Okay. Find my calculator over here. Okay. So now from here, let me use my hat to balance it. I have 48 minus 45, which is 3, divided by 0.76 equals 3.9473. So equals that. I'm going to round that again to 3.95 to 2 decimal places. So that equals 3.95, which is what my Z-score is. Woo! So Z equals 3.95. Now, there are our next step is to make a decision, determine whether we're going to reject or retain the null hypothesis. So one thing that I want to state before getting into this is that there are 2 different pairs of information that allows us to make that distinction, to make that decision, I should say. We can use our Z-score, the one we just calculated in step 3, where we got 3.95, and compare that to the critical values of plus minus 1.96. So I'm going to draw kind of how we would do that. Oh, okay. So here's a distribution here. It's ugly, but it does the job. So we have a distribution here where I've graphed out the critical values. Here's negative 1.96 over here and positive 1.96 over there. If I were to plot my Z-score, which again, we just calculated in step 3, just prior to this part, I would plot that on this particular distribution. So, 3.95 will be like over here somewhere. Okay. So, you can't really see, but it's going to be shaded, shaded, shaded. Any place where if our Z-score, if our test statistic falls in that shaded region, like our 3.95 does, we are going to reject the null. And same thing if it were to be negative. If we had a negative 3.95, that would also fall in this shaded region just on this far corner, far end, and we would reject the null there as well. If it's anywhere in this unshaded region, we would retain it. Okay. So we're not retaining the null because we see that our 3.95 falls way past that shaded region. So our decision would be to reject the null hypothesis. Now, I mentioned there's two pairs of data to determine significance. It's our test statistic, in this case, our Z statistic, our Z score, paired with the critical values that we wrote down for step 2 for setting the criteria, that plus minus 1.96. We can compare critical values and test statistics, and our other pair would be to compare the p-values with alpha. So our alpha was set at 0.05. We don't know our p-value yet. Now, we are going to be, Z-scores are the only tests that we'll be covering in this class where we will be calculating the p-value by hand. However, I do want us to know how to use the p-value to determine significance because that's important. I want you guys to know that. It's going to help you with your GE assignment later on in the semester. And it's just good to know going into 144. So with the p-value, we take we're going to use the trusty Z table, and we're going to go to our calculated Z statistic of 3.95. Think of that when we're using p-values, think of that as a reference point, that 3.95. So we have our Z score of 3.95. We don't have a specific place on our table. So pick your poison. The difference between the C columns, which is where we are looking to find our p-value, the difference between the C column for 3.9 and 4.0 is negligible. You see it's dinky either way. So I'm just going to do with 3.90. So let me move my mouse. So that gives me a point. Just a second. I got to figure out a place to write this on here. 0. How many zeros is that? 0.0005. Okay. So again, where did I put it? Okay. So I got this from the Z table. Now I'm not quite done yet. Since this is a two-tailed test, we've split the significance on either side of the distribution. It can be high, it can be low, just like our critical values show. However, when we're calculating the p-value using the Z table, we need to give that back. So we split it in half before to distribute it evenly on each side of the distribution. Now to find the true value of p, we will multiply that by 2 to kind of give it back. So to find the p-value of a Z statistic for a one sample Z test, we are going to look in the Z table for our corresponding Z score. Whatever we see in column C for that Z score, we would multiply by 2 for a two-tailed test. So let me do that really quickly. So it was 0.0005 times 2 gives us a p-value equal to 0.001. Okay. So we compare that p-value to alpha, which again is 0.05 or 5%. So when it comes to p-values, I have it over here. When it comes to p-values, think of alpha as a limbo bar. I've personally never limboed myself, but the premise of limbo is you have a sort of, bar, a limbo bar, and your goal as a limbist, a limbo player, I don't know, you want to get under it. You want to be a significant limboist, limbo player. I don't know how to put it. But to win your round of limbo, you need to get under it. If you hit the bar, doesn't count. You don't proceed on to the next round. You need to get your whole body completely under it to proceed, to be a significant limbo player, limboist, whatever. P-values work the same way with alpha. Alpha is our limbo bar. In this case, we set it at 0.05. For us to have a significant p-value, for us to reject the null hypothesis, p needs to be below that bar. For us to retain the null hypothesis, for it to not be a significant limbist, we would have to have our p-value above alpha. So imagine this black bar as our alpha, or well, it is alpha, but our limbo bar, it is set at 0.05. And to have a significant p-value, for us to reject the null, our p-value needs to be underneath that limbo bar. Again, to be a significant limbist, you need to go under. If it's not significant, if we were to retain the null, the p-value would be above it. So it'd be bumping against it or just walking over the thing. So for us to have a significant p-value, for us to reject the null, it needs to be less than 0.05, our alpha. Again, those two pairs of information that we have to determine significance, to make the decision regarding the null hypothesis, we have p and alpha, and then we have, oh, correct. I didn't mean to do that. And then we have our z statistic, or whatever our test statistic is, and our critical values. And I've graphed that here. So this is the critical value and test statistic notion. And I guess you can think of this as the p-value and alpha. So again, we have our p-values, or our alpha, set to 0.05. Our p-value was 0.001. That is indeed below our alpha bar. Yay! Right here. So regardless of what method you use, you are going to make the same conclusion. You will be making the same decision when it comes to the null hypothesis. Using our critical values and z statistic, we determined we would reject the null. And using alpha and our p-values, we also determined we would reject the null. They should match. They should both be making that same conclusion. So with that being said, we do reject the null. So now we want to calculate Cohen's d, and then I want to determine the strength of the effect size. What is the strength of the Cohen's d that we're going to calculate? So I'm going to erase my p-value stuff over here as well. No, I'm just going to erase this because I need room to calculate Cohen's d. So here, I'll kind of leave it on screen for a bit. So if you want to use it as a reference, pause it, cherish the moment, whatever. But I'm going to erase that, and then I'm going to calculate Cohen's d. Okay, so to calculate Cohen's d for a one sample z test, there's a lot of rhyming at this point in the semester, and it gets me all tongue-tied. My rap career never took off. So what we're going to do is, the formula to calculate Cohen's d is sample mean minus population mean divided by the population standard deviation. That's how we would calculate it for a one sample z test. So to do so, we are going to plug the information into that formula. So our sample mean was 48, our population mean was 45, and our standard deviation for the population was 12. So we have 48 for our sample mean. We got that over here. We got 45 for our population mean right here, and 12 for our population standard deviation, which we got from right here. Okay, so that gives us 48 minus 45 is 3. 3 divided by 12 is 0.25. Can't really see that 5 very well. Just a moment. Okay. So here we go. Over here, 0.25 is our Cohen's d. Now, a couple things. Based on the thresholds of strength, my apologies, a Cohen's d between 0.2 and 0.8 is medium. So this is a medium strength. Now, keep in mind there's strength and there's direction of Cohen's d. Strength is just the number 0.25, 1, 7, whatever it is. The direction refers to if it's a positive or negative value. The direction does not impact the strength. Imagine there is a wall between them. They do not cross over. So if we were to have a negative 0.25 Cohen's d, that would still be medium. The direction, that negative, does not change the strength. It's not weak now that it's negative. That's got nothing to do with it at all. That's like comparing apples and oranges. It's, gee, my apple's got a weird, why doesn't my apple go good in my orange juice? Because it's completely different fruit. Like they don't impact the other there. So what we do is, again, I mean, this is a positive Cohen's d, so this isn't so much an issue for students, but a lot of times if I were to have a negative 0.25 or its negative counterpart, that strength would still be the same. Do not make that mistake. I've seen it too often, and just, do better. Anyway, so with Cohen's d, one last thing that I wanted to talk about was knowing if your Cohen's d is significant or not. Now, this is really easy since we've already completed the null hypothesis testing for our one sample z-test. Basically, it boils down to if you rejected the null, Cohen's d is significant. Doesn't matter how big or small it is. If you have rejected the null, if that was the decision you concluded to in step 4, you reject the null, Cohen's d is significant. If you did not reject the null, if you retained the null or failed to reject, if you've heard that statement as well. But if you retain the null, Cohen's d is not significant. Doesn't matter the size or the direction at all. The only way to determine if Cohen's d is significant or not is just looking at the decision you made in step 4. So since we rejected the null, since we concluded that our null hypothesis is to be rejected, that means that our Cohen's d value is significant. So I just wrote it underneath there, significant. And that's that. So if you have any questions, if you're struggling with it, let me know. Email me before that due date if you can. But ultimately, that is how to calculate one sample z-test. So make sure to do the rest of the activity on your own. They're going to be a little more complicated, but just read the questions carefully, label the information it gives you. All the information you need to calculate the z-test is there. So good luck, and I'll see you all next time.